This is lecture 126 of Tech Talks. We'll be covering the LM7900 series 3-terminal negative regulators. We'll be covering the LM7905, the LM7912, and the LM7915, made by Texas Instruments. We have features of a thermal short circuit and safe area protection, high ripple rejection, 1.5 amp maximum output current, and a 4% tolerance on preset output voltages. The IC is contained in a TO220 package, and it's just like the 7800 family series, except for the pins are a little different. Pin 1 is ground here instead of input. Pin 2 is input instead of ground, and pin 3 is output, and that's exactly the same. So, things to remember on this is that it required if, we're looking at this little star here, we come down to here, we see that right there, and it says required if a regulator is separated from the filter capacitor by more than 3 inches. And this is on your board layout. For a value given, capacitors must be solid titanium or a 25 microfarad aluminum electrolytic may be substituted. For the output cap, we have this little warning: required for stability. For value given, capacitance must be solid titanium or 25 microfarad aluminum electrolytic. It's paper cap. May be substituted. Values given may be increased without limit. For output capacitance in excess of 100 microfarads, a high current diode from input to output, a 1N4000 series, which we had covered in previous lectures, and this is where the peak inverse voltage would come into play, will protect the regulator from momentary input shorts. We're going to cover the maximum ratings. This will be what determines what your step-down transformer will produce. So from the 7905, the negative 5 volt voltage regulator, the maximum input is a negative 25 pulsating DC, which we'll go over after a little while. The negative 12 volt and negative 15 volt, the maximum input to it can be a negative 35 volt pulsating DC. The operating temperature is the same as the 7800 family, is 0 degrees Celsius to 125 degrees Celsius, and this can be called centigrade as well, but that is an older term. Then we'll go into the different, for each lecture, the 20 lectures, 126, 127, will be over negative 12 volts and negative 15 volt consecutively. Right now we're going to go over the LM7912. The LM7912 voltage regulator, electrical characteristics under this testing parameters: I out equals 500 milliamps, CN equals 2.2 microfarad, C out equals 1 microfarad. Temperature operating range is from 0 degrees Celsius to 125 degrees Celsius. Power dissipation is less than 1.5 watts. The part number is 7912C. Output voltage is a negative 12 volts with a pulsating DC in of negative 19. The voltage out at 25 degrees Celsius will vary from a negative 11.5, typically 12, to a maximum of 12.5, depending on the load and the voltage of the pulsating DC in. The delta out, V out, will vary from 5 to 80 millivolts, depending on the DC, pulsating DC in. The load regulation, depending on the current, will vary from the current. When the current is between 5 milliamps and less than 1.5 amps, it will vary from 15 to 200 millivolts. And when it's between 250 milliamps and less than 750 milliamps, will vary from 5 to 75 millivolts. Quiescent current, that is the current that it has when it's at rest, it's not supplying for a load, is 1.5 milliamps. output noise rejection of 120 hertz is 300 microvolts, and it has a dB reading of 54 minimum to 70 dB rejection rate. The peak output current is 2.2 amps at 25 degrees Celsius, and the average temperature is negative 0.8 millivolts per degree Celsius. And as we know, that TJ, theta TJ, will be 19 degrees Celsius per watt. It's just like the 7800 family series. Okay, moving on. All right. As you can see here from our circuit diagram that we have here, it looks like the one that we used on the 7800 family series. And it is exactly the same, except for one minor detail. We have the same AC voltage in, 120 volts AC in. Our step down transformer to 25 volts AC here, represented by there. That goes into our full wave rectifier. Now this is different because we want negative voltage here, not positive voltage. So we've rotated this full wave rectifier by 180 degrees. And now the anodes are connected to our input to the regulator, and the cathodes are connected to ground. That makes this our rectifier output, our peak voltage, and we go into the same bulk capacitance. Our capacitor is large enough, it'll work. And then we filter that out. That feeds into pin 2. Now on the 7800 voltage regulators, pin 1 was the input, but here pin 1 is the ground. Pin 2 is the negative input, and we got a negative 25 volts coming in. And we'll have our negative 5 volts out. This is our output last filtering capacitance, and it's a ceramic cap. Okay, that's a complete review of the power supply schematic. Let's dissect this schematic one piece at a time, starting with the power transformer. The minimum amount of voltage in to cause the regulator to work is what we could set the secondary of the transformer to. We're going for 25 volts. It does not exceed the maximum input, and it's well over the minimum input. The turns ratio of this is very easily found by taking the 120 volt input and dividing it by the 25 volts output, which makes a 4.8 turns ratio. The next section of our schematic is the rectifying section. It is a bridge rectifier developed by Leo Graetz, who was a German physicist who lived from 1856 to 1941. Graetz. The full wave rectifier is a circuit of 4 diodes that converts alternating current into direct current. It achieves this by using 2 diodes to conduct current in one direction during one half of the AC cycle, as you can see in the diagram, and then the other 2 diodes to conduct in the same direction during the next half cycle, effectively full wave rectifying the AC input. The function converts the low voltage AC from the transformer into pulsating DC. A full wave rectifier is the most efficient choice, but you can use a half wave rectifier, which just uses 2 diodes. You can use 1N4007 diodes, and this is where the peak inverse voltage that we talked about in lecture 119 comes into effect. So let's go to QUCS and see if we can create this circuit for simulation. Okay, now we want to use our QUCS to do a simulation on the Graetz full wave rectifying bridge. We don't want to redesign the QUCS, but so let's go to the QUCS website and look at some of their examples and see if they have an already put together project just for that. So I'm going to use Google search engine. I'm going to type in LabRats Engineering, LabRats engineering.com to get to our website, and that'll have a link to the help files on the QUCS. And as you can see, there's many things you might want to check out. But we want to go to lab components, simulating tools. Kind of goes over what we have there. Here's our QUCS simulator link. Takes us to the home page. We go to the download section. We go to examples and build instructions, install instructions. Let's go to examples. Scroll down and see if we can find anything to do with the Graetz full wave rectifier. I don't see anything right here. I know it's here though. So scroll a little bit slower. Here it is right here. Full wave rectifier to Graetz bridge rectifier, a full wave rectifying using 4 dot. That's what we want. Left click onto that. It downloads it into your download file. Open that up. It's right here. Copy that. I've done it twice. Copy. Now I need to get to my .QUCS folder. It's a hidden folder. So I know where mine is. It's on the C drive. Under users, administrator, .QUCS. I double click, get into that, and I just right click, paste in this directory, and it will produce this right here, and that's that result. That's how you get it into your folder. Then we'll close these up, close that up, start the QUCS bat. Alrighty. Now I have, go over to here, I say open recent. I've got the full wave rectifying schematic. Click on that, and I've already set it. It's already set up. It's exactly what we want. And we got this has a 220 volt input. I'm going to go to this. I'm going to close that and open up this project. Now here is the positive. This would produce a positive V out. As you can see, here's our pulsating DC, and this is our sinusoidal input, 120 volts, 60 cycles. You can go through this and look at all the added properties, excuse me, and see how they set this up so that you can do it yourself. But we're going to hit execute to run the thing. There's no errors. I go to display page. Right here, there's no errors. And we see that this is what we're getting now. We're getting this blue input of 60 cycles, 120 volts. It's reducing it down. It's a 1-to-1 transfer. It's not reducing it at all. And it's putting out 120 volt AC out. So it's not a step down. There's no turns ratio. It's a 1-to-1, as you can see right there. But you get to see how the diode, the full wave rectifier, is working. Now I want to show you a little trick. We're going to go here. We're going to click on this diode. We're going to right click. We're going to say rotate once. Rotate again. Do that with all 4 diodes. Rotate once. Rotate again. Left click. Right click. Rotate. Right click. Rotate. Left click. Right click. Rotate. Right click. Rotate. Now we're set up to put a negative voltage out here. We rotated this, as I explained in the schematic, 180 degrees. We'll hit the execution simulation button. No errors. Go to display page. Everything's cool. And now you can see how our pulsating DC voltage is negative compared to the other one, which was positive. And so this, we can simulate this. We did, and we've seen the positive and negative. So anyway, we're moving on. All right, since we have a working model of a pulsating positive DC output of the full wave rectifying bridge, let's add a capacitor and see if we can simulate that and see our ripple and the bulk capacitor doing its job and seeing what that voltage will be feeding into the IC itself. So to get a capacitor, I need to go to get my components, come over here, hit select components. This is lump components. And remember, I had this a source of all kinds of stuff. I click on the capacitor and bring it over, drag it over to the schematic area. Right click, I want to rotate it. I want to edit the properties of it, and I want to make it a 100 microfarad capacitor. Get rid of the P, put a U there. That's short for the microfarad. Apply. Okay. Drag. What in the world is wrong with this? Drag this over to here. So it's between the diodes and the load. Our load is a 1K ohm resistor. We go up here to the wire wrapping tool. Click that. Put it on the red dot. Drag to that line above. Left click. Do the same for the bottom. Click. Drag. Click again. Hit the escape button. Get on the cursor. That's 100 microfarad. Let's make sure it is. We'll hit apply again. Okay. Let's hit the execute button. No errors. Go to display page. See if there's more errors. There's no errors at all. Go to the full wave rectifier. Let's see. Let's go to here, right here, and check that out. Isn't that cool? Yeah, you can see the ripple from the pulsating DC, but it's been filtered by the bulk capacitor. And now this will be the voltage that will feed into the IC. Now we'd have a step down transformer of 4.8 for to put in 25 volts AC, and this is a 1-to-1, so we got 120 in, 120 out. But with a turns ratio of 4.8, you would divide the 120 by 4.8, and that would give you 25 volts AC, and that would feed into here, and then this would be 25 volts filtered out like that. Let's try that again with the negative. I've actually already done it. We'll see if we can open it up. Here's the full wave rectifier with a bulk capacitor of the negative way, and check that out. There is our filtered DC, pulsating DC. Works like a champ. Okay, very good. Let's move on. There's a couple things you want to remember about placement of the capacitor. This is an electrolytic capacitor, so the curved side of it will be curved like that, is connected to the can itself, and it has heat shrink around it that isolates it. But on the very top of the can, you can see the aluminum can, and then that will have voltage on it if you don't have the curved side going to ground. But that's okay. The first time you apply voltage to a electrolytic cap, that is when it polarizes the cap. And then from then on out, you have to use it that way. So that's why it didn't matter which way we put this cap, because it's a simulation. It's not a real cap. And but just keep that in mind. And also keep in mind that you want this capacitor as close to the chip itself as possible, within 3 inches. Okay, moving on. Concerning this transformer being a 1-to-1, so we're getting 120 volts in and 120 volts out. We don't want that. We want 120 volts in and 25 volts out. So we take our calculator right here. We will go ahead and calculate it. So 120 divided by 25 makes 4.8. So that divided into 1 gives me 0.2 0.208333. So I come over to here. I convert the 1 to 1 to 0.208333. It's repeating. Just do it a couple times. Hit apply. Say OK. Come up. As you can see, the graph right now is we have 120 volt filtered out. So we'll hit the execution button again. Everything worked. Close the window. And as you can see here, now our reduction has occurred. We have 120 volts in, and we have a filtered pulsating DC of 25 volts out. It's pulsating DC because the capacitor is there, but it's filtered now by the bulk capacitor. Okay, that's it. Thank you. Again, here's the picture that we had of the bulk capacitor. And you can see the ripple. You can see the pulsating DC in up to the negative voltage that we would have, which is we have a 4.8 turns ratio transformer, which makes that 25 volts. You can see the ripple, the maximum DC value, the ripple, and the pulsating 2 full cycles of the AC input. And we saw through the simulation that the simulation worked exactly like the picture said, and was actually a little bit less ripple than what we had here. Okay, moving on. For a quick review of what we've already covered, we covered the transformer, which is a step-down transformer from 120 volts AC, 60 cycles, to 25 volts AC, 60 cycle. Graetz full wave rectifier, which creates a pulsating DC of 25 volts with a ripple of 120 hertz. C1, C2 are bulk capacitance, which filters that pulsating DC into a filtered DC. Remember that this time constant of the charge rate of the capacitors must be greater than the wavelength of the frequency coming in. Then we're going to go over our voltage regulator at the 7905 negative 5 volt regulator. And we're going to try to simulate that. So let's break off and do that right now. Okay, now we're going to do our simulation. I can't find a SPICE model for the LM7805 or the 78 family or the 7900 family. All I could find was under libraries this LM337K, which is a Texas Instrument negative voltage regulator. So we're going to use that, and we're going to open up the project we had before. I use this project here, and I called it Full Wave Bridge Rectifier. It's a Graetz Full Wave Rectifier. We'll start with the positive side. Remember, this was 1-to-1 on the transformer, so I had to do it to 4.8 to 1 turns ratio, which you remember you have to go in here and click edit and then change the turns ratio to the proper amount. From 0 it's a step down, so you divide it into 1. Then we added this bulk capacitance as well. And remember, we got this circuit for a rectifier circuit, the Graetz bridge rectifier, from the QUCS examples, which if you go through my website, you can find your path to that. Knowing this and rectifying it, we see that we got our 120 volts out. We've got a nice 5 volts filtered DC. This cap was added to change the pulsating DC into a filtered DC. So let's go to the negative equivalent. Now remember, to get the negative equivalent, you have to rotate all your diodes by 180 degrees. And as you can see from this, we're getting a real nice, pretty 5 volt filtered DC out. But we want to add our regulator, our LM337K, and we can do that. First, you want to left click onto the schematic somewhere and say set on grid. That will help when you're wire wrapping your components up, because it makes the component snap to one of the dots. Also, you want to edit the document, change your grid to 5 vertical, and horizontal. Apply it, say OK. Now that gives you more resolution as you're building your schematic. The next thing to do is go to the libraries, go to the regulators, it'll look like that, open it up, drag the 337 over, drop it in. You don't have to edit any properties, and I dropped it to here. Now remember, we're using this schematic right here for our representation. That's how we're going to wire this up. We know that R1 is going to be 120 volts, so we got to calculate R2. We do that by going down to here. It gives you several example circuits you can build to use for this. The SPICE model emulates this right here. So we know R1 is usually 120 ohms as part of the resistor divider. We're going to use this equation right here to determine what R2 is going to be. So we bring our calculator here. V out is going to be a negative 5 volts, and divide that by a negative 1.25 divided by 1.25 equals 4. 4 minus 1 is 3, and 3 times 120 is 360 ohms. We need a 360 ohm resistor. So bring that, and that's what we'll get 2 resistors. I took the one that was right here, that 1K. I brought it over to here, converted it to 120 ohms. I copied it, pasted it again, and did edit, change it to 360, applied it, said okay, wired the component like it's supposed to be wired, and the schematic diagram example. Came up to the execute simulation tab here, and I hit that. As you can see, it executed again, 0 error, so that means you can do it. Close the window. Here you can see the input voltage. Here's your filtered DC 25 volts out, which is a pulsating DC here. I created this diagram here. I go into the edit. I'll show you how to go over here to the library or components. Go to diagrams, which is down here. Bring in a Cartesian graph. Then I would once I executed the simulation, these get populated. I say I want to see VTN, which is right here. And I want to see the pulsating DC out. I hit apply. Say okay. And that's what I got here. And that's exactly how I got this here. So I don't need that. I'm going to delete that. Didn't mean to do that. I just want to delete this one. Sometimes you got to make sure you're not touching some. And I did the same with this here. But I have a V out here now, and then I have the V adjust here. And as you can see, I got a not real smooth negative 5 volts out. And then this is the variable adjusting voltage here. So that takes care of this. That shows you what it's supposed to do, how it works, and that includes everything. Now we got to calculate, do we need a heat sink or not? Okay, open up your PTC Math CAD. Open up the worksheet you used for the 7800 family, power dissipation calculation. You should have saved it. Using the formula PD equals VN minus V out times I out will give us our power dissipation. Our VN, as you can see, is 25 volts DC filtered. It'll give us 5 volts out at 1.5 amps. So 25 minus 5 times 1.5 is 30 watts. That's high. That's 30 watts across that chip. That's going to get hot. We can recall that the theta junction ambient is 19 degrees Celsius per watt. So we take our delta T equals the PD times theta JA. So that's 19 times 30. 19 times 30 is going to give us 570 degrees Celsius. That's extreme temperature there. So let's see. We got to add the ambient temperature to that as well. So we add 40 to the 570 degrees Celsius. That gives us 610 degrees Celsius. That's impractical. That won't work. So we have a problem. We need to find a solution. One thing, if you'll recall, is that this VN only needs to be 2 volts greater than the V out. So we'll go a little bit more than 2. We'll make it 5, and we'll reduce this to 10 because it's probably an easier transformer to find. So now that gives us a wattage of 7.5 watts. It dropped considerably. So let's take the 7.5 watts, multiply it by the 19 degrees Celsius per watt. That gives us 142 degrees Celsius versus 570 degrees Celsius. Well, we got to add the ambient. And the ambient is 40 degrees average, so it'll be 182 degrees here total. That is degrees Celsius. That's the temperature that will be dissipating inside the chip. The chip can go up to 125 degrees Celsius, but with a common case, 220 case heatsink, it should easily dissipate this temperature now. So now we got more practical design, something that can be met with common components. Okay, that's it for this. Enjoy building this if you're going to do that, and we'll continue on. Okay, since I didn't do the negative 12 voltage regulator simulation, and I can, and I've just found out the LM337KC that we have is actually an adjustable power voltage regulator. So we can go from negative 1.2 volts to negative 37 volts. So let's do it. Well, this is the layout schematic we're going to be using, and we have to just vary R2. So we need to find R2 to produce a negative 12 volts. We have a TO220 case. Here are the different characteristics of the device, which we went over earlier. Here is what the SPICE model is modeling. Here again is our schematic we're going to be using. We know that R1 is 120 ohms. So we're going to calculate R2. Open calculator. So V out is going to be a negative 12 divided by 1.25 negative will give you a positive 9.6. Minus 1 gives you 8.6, and times 120 gives you 1,032 ohms. So that's what we're going to change R2 to. So let's lower this down. We'll bring up the QUCS, and this is already had this built. We got R2 at 1,032 ohms, R1 at 120 ohms. We got a probe here, a voltage probe to measure our output, and we're going to do a simulation. Run the simulator. We have a problem. There's a ground is missing. So there it is. Somehow I got deleted, but it's back. We'll do the simulation. Excellent. Everything worked. Close window. We'll go to our display. We have our 120 volts in to the primary. Out of the secondary through the filter cap, we have the filtered pulsating DC of 25 volts that goes into the regulator here. And out from the regulator right here, we have the red line, which is negative 12 volts, because we can see this from our table, from the voltage probe table. And right here at V-adjust, we have just a little bit lower than that 12 volts. So it works. It works fantastic. So, and enjoy using that, and good luck. Thank you.